Okay. So, in the last class we had looked at time and we have seen two types of representations. One is TI, another is UTC. Now, in many situations when we have got multiple computers working for solving some problem, which is also a very realistic situation in the present day embedded systems, when there are multiple processors working for the overall objective of meeting some constraints or delivering certain things. For example, in the automobiles there are different dedicated processors for different tasks. So, there is a necessity of synchronization between the clocks. Whenever I have got more than one clock, I need to have a synchronization among them, so that they count together, right. So, if I have one master clock, one thing is that I have got one master clock and everybody is adhering to that master clock, then that is fine, okay, for internal synchronization. In other situations, when there are distributed synchronization, there is also internal synchronization. Then we collect the information from the neighbors. Say for example, I get its time and I first collect the information from the neighbor and then apply the corrections, and get the correct value. Okay. So, that means as if I want to check my time, I ask you what is the time, and accordingly I adjust my time, like that, and we set the correct value. That is how we do for internal synchronization. So, for example, this process will seek the time from here and will correct it itself. Now, the precision of this, that is collecting the information from the neighbors, how frequently that will be done, that varies from the application level. For example, if it be at the application layer, then it might be at the level of microsecond, for example, around 500 microsecond to 5 millisecond. At this interval I want to check. Whereas, if I come to the communication hardware, it becomes much more faster. For example, whenever I come to communication hardware, then it is less than 10 microsecond. I communicate much faster. At the kernel level, for example, when I come to the kernel level, it is somewhere in between like 10 microsecond to 100 microsecond. Sorry. All right. So, the precision of step, whenever, I mean, these are the levels of precision that I want, that the match between this one and this one at the application layer, let me write it down, at the application layer, it should be within this, which should not, the error should not be more than this, whereas for the communication hardware, it should be much more accurate. That is for internal synchronization, but sometimes we also do external synchronization. In external synchronization, what we do is we usually use a GPS. Nowadays, the trend is to use a GPS. The GPS actually offers both TAI and UTC, both timing informations are provided, and we take the GPS and synchronize with respect to that. All right. And in this case, the resolution is of about 100 nanosecond. Okay. 100 nanosecond resolution. So, that is how we deal with this. Now, what are the things that we have done? We have seen what are the characteristics of the operating system. a real time operating system. One is it must be predictable, right, the requirements. Number 2, it must be doing the task of scheduling. We will look at scheduling in much more detail later. And third, it must be very fast. The operating system must be fast because of meeting real time constraints. It should not take too much time to make the decisions. All right. So, given this, now then we saw that how we carry out the synchronization and all those. Next, we move to the structure of the real time kernels. So, we have already seen in the last class that we had a layer of like this, that the application layer was there at the top, and the real time kernel was at the bottom. Real time kernel was at the bottom, and there were device drivers on this stack, right. Device drivers were there, and then there was some middleware. And the application software was running on this. That was the scenario compared to the operating system coming in between these layers in the case of a standard operating system. Now, the general now this can be thought of as a general RTOS, real time operating system, or there can be RTOS for specific domains. I can have specially tuned real time operating systems as well. Right. So, the classes of real time operating systems are one is fast and proprietary. There is a not open kernels. Okay. A typical example of this is the VxWorks. All right. Now, what is the advantage of these, which are proprietary, made for a particular domain? That they are fast, but they are not predictable. Typically, it has been found that they are not predictable for all situations. They have been designed specifically for a particular application, tuning it so that it is fast for that, and that is a proprietary kernel. But it has been found that it has not been tested for all the situations. Therefore, the predictability still remains an issue in this case. The second category is the RT extension to standard WES. We are extending the standard WES to generate RT. Now, I will draw a diagram which will illustrate something interesting, some of the advantages of this. Say, I have got a real time kernel at the base. Now, I am creating two compartments here. On this side, on this I have got my device drivers. All right. So, device driver 1, device driver 2, and on this I have got real time tasks, say real time task 1, say RT task 2. All right. On the other side, I have got the standard OS running on this kernel. Okay. Running on the same kernel, and on this side I have got non-RT task. All right. Now, what is the advantage of this? If I, often in your PC or in Windows machine, the system crashes. Even if there be a crash of the standard OS, the real time tasks will not be affected. Okay. The disadvantage is that the standard, there are some facilities or some functionalities given in the standard OS, but the real time tasks, these cannot access those functionalities. They cannot access those functionalities, right. That is a downside of this. Okay. But this is fine, but like one typical example of this is the RT Linux, which is built on the Linux kernel, but these are the problems that occur in that case. And of course, because of the standard OS, it is a little heavy and it is not that fast as the proprietary kernels are. It may not always be the case. In that case, what can happen is that the question is that why is it that the device drivers are not accepted by this? Now, in my diagram here, under the standard OS, there are device drivers also. There are device drivers in this zone also. Okay. But these device drivers are under the control of the standard OS. Therefore, whenever a task wants to access this device driver, that request has to be routed through the standard OS, which can establish mutual exclusion, which can make you wait, all those things. But that is not a desirable situation, and neither is it a required situation for many real time tasks. So, the dedicated devices I can keep out of the purview of the standard OS. Okay.
If some devices in this part, if a standard OS want to use them.
No, that is the problem. That you can't do. That you can't do.
So, how we can categorize that?
No, that's why it is it's not a general OS. Whenever there is a general OS part, only up to this part, the general OS part, and this part is a real time thing, but they are using the same kernel. Okay. So, I had the real time, I had this standard OS initially, I had the kernel, I extended this and have connected my device drivers on this, so that my real time operating system, real time tasks run on this. Okay. I will show you another example for this. Say for example, I have got the hardware here. And on this I have got the say real time Linux, in which there is a real time scheduler. All right, our scheduler is there, and I have got real time tasks. These are communicating with this scheduler. The scheduling policy of the standard OS will be different from the real time scheduling policies also, we will see that soon. And So, this is communicating through some interrupts. And on this side, I have got the Linux kernel, where I have got a scheduler, and there are drivers here. The drivers are connected, I mean communicating via I/O operations with the hardware through this kernel, and they can also connect through interrupts here. All right. And on this are my very well known processes like say init, bash, or maybe Internet Explorer, whatever, or Google Chrome, they are running on this. All right. Now, if there be any crash on this part will not be affected. All right. So, here I have got a separate scheduler for both of them. The reason for having a separate scheduler will be evident soon, when we will see that maybe the next couple of lectures, when we will see that the scheduling policies that we are familiar with regarding in standard OS are always not applicable for real time operating systems. So, yes.
By both this normal Linux and this RTOS, RT Linux,
Needs to sit in the same system. I mean, so for example, if you want, no, that is just an idea. For example, the question is that as this diagram is showing, it is the same hardware is being shared by both of them. It is not the case like that. The case is that forget about the hardware, I can separate out the hardware. There can be an embedded system which is on this. We are right now discussing about the operating system part. Now, this operating system that has been designed to coexist along with the general operating system. So, this part, let me put some other color. These two are as extensions. The red ones, these ones are extensions, as was shown in my earlier diagram. Where did it go? Yeah. So, in this diagram. So, the operating systems are sitting on the kernel, but the standard operating system is using some kernel functions, the real time tasks are accessing some other kernel functions. The device drivers are separate, and the non real time tasks are accessing the kernel through the standard operating system. All right. And this one has got the option of not going through the standard operating system, that is all. Now, whether the type of diagram that I had drawn here, that as if they are on the same hardware, that is not necessary, because for an embedded system, I do not expect that the same hardware will be loaded by a non real time task as well as a real time task. Okay. So, this hardware can be different, actually will be different, but the point is that how the operating system interacts with the hardware. There are two separate paths for doing that. That is what is being proposed. So, with this we have looked at the requirements of real time operating systems in general. Now, we will look into some other aspects of real time system. Gradually, we will move to the scheduling part, but before that, as has been said, that timing and predictability are two very important issues for real time operating system. One of the major impediments to predictability is resource sharing. For example, you want a resource and you may not get that resource, right. So, how do you handle that? Or so, this problem of resource sharing we have also encountered in the normal operating system course, right, where we let us quickly revise what we mean by critical section. Okay. What is critical section? Critical section is that part, say here is my code, the piece of code that interacts with a shared resource that is used to access some shared resource, for example, a driver. All right. That driver is accessing this shared resource, and there is another thread of the program which also wants to access the same shared resource. Now, for that it will use the same driver. Now, are we going to allow both of them access this piece of code at the same time? That implies that we will be accessing this shared resource simultaneously, which often may not be admissible, because if there be a two writes or one read one write, then the results can be unpredictable and the results can also be erroneous. So, we need to employ some sort of mutual exclusion over that, and we know that in order to ensure mutual exclusion, for example, there is let me call it task 1 and task 2. So, when task 1 executes, before it accesses a critical section, it performs a P operation. P means the wait operation, P S, where S is a semaphore, is equivalent to wait on S. And you know that this semaphore is nothing but an integer on which only two atomic operations are applicable, only two, and they are signal and wait. Now, the critical point here is that each of them must be atomic. That means, when a process is performing wait S, then another process cannot perform wait S or signal S on this particular S. S is a particular semaphore variable. All right. And what does wait S do? Wait S simply decrements the value of the semaphore by 1. So, suppose process T1 is executing and here it wants to enter the critical section. It wants to enter the critical section here. It performs a wait. Suppose, just for those who might not have done an operating system course, I am just repeating this, but I am sure most of you have done that. Suppose the semaphore S was initialized to 1 and semaphore S is a shared variable. Okay. Now, when I do P S or wait S, that means this value of S gets decremented to 0. And suppose now T2 also starts, and at this point T2 is starting a little late, maybe T2 has started a little late, and sorry, not here, maybe somewhere here T2 wants to enter the same critical section, same driver it wants to access, same resource it wants to access, and it tries to do a PS, because this piece of code is protected or gated by the safety valve S, semaphore S. All right. So, what happens is now, but the resource is already occupied by T1, therefore, value of S is 0. The function of weight is, what I said was a little incomplete. The function of weight is, it will first check whether S is greater than 0. If so, it will decrement it. Otherwise, it will continuously wait on this value to be 1. Okay. Clear? Weight is actually first checks the value of S. If S is greater than 1, then decrement S and proceed. Otherwise, go on checking the value of S till it becomes greater than 0. So, since the task T1 is inside this critical section, task T2 is trying to enter that and is doing this PS, it cannot enter. Okay. And when this one completes the task of the critical section, it performs VS. VS is equivalent to signal S. Signal S means S plus plus. So, it increments S, right. I have skipped some of the details of weight S, because this busy waiting, that one process T2 for example was continuously checking the value of S, that overhead can be avoided by putting them in a queue, and those details, implementation details, I am not discussing. Those details are basically operating system issues, and there are different ways by which interrupt can be utilized in order to get rid of this thing called busy waiting. All right. Now, so when this one comes out of this VS, when this thing comes out of this VS, then this one will succeed. Now, suppose here again T1 wants to enter the critical section. So, it will perform a PS, but this is still going on. So, at that point this is locked, and since this one has got done VS, this PS has succeeded. Therefore, T2 is now somewhere here, T2 is somewhere here now. When T2 exits this point, say here T2 does VS, only after that this can go in. Therefore, on the shared resource, on a particular shared resource that has been gated by S, is being provided mutual exclusion by the semaphore S. All right. Say the resource R is being protected by the semaphore S. Therefore, although I am, so what can be the consequence of this in terms of real time performance? I do not know the a priori what resources a task actually requests for. So, we will see how the timing of task gets affected because of this critical section issues. Okay. Let us,
Are there different S for different resources?
are there
Different S for different resources?
are there different S's for different, yes, because these are the different, typically that should be the case. Whether we should keep, the question is whether we should keep separate semaphores for protecting the separate resources. Yes, that is the actual practice. Otherwise, there will be completely race condition. I mean, one resource is being freed, but another one which is waiting for some other resource will get that. So, there should be separate semaphores. The semaphores may be binary, may not be binary also. For example, maybe in a particular application, I may like to allow, say some application. It really does not matter if 3 processes can go in simultaneously here. I can allow 3 processes to go in, but not more than that. So, in that case, say I make it another semaphore S1, I can initialize it to 3, right. So, whenever the first process P1 wants to get in, it does PS1 and S1 becomes 2. That means 2 more can still go in. Thus, this value of this variable can also be utilized to know at any particular point of time how many processes are there inside the critical section. Okay. Now, let us take an example. Let us right now consider 2 tasks T1 and T2, and we assume that the priority of T1 is greater than the priority of T2. All right. So, this means let me write down priority of T1 is greater than the priority of T2. Now, here I am talking of priority scheduling, but before going into that, let me talk about, I will come back to this in a minute. Before that, let us talk about scheduling. Scheduling can be preemptive or non-preemptive. What is the meaning of that? Even before that, when we schedule a task, what do we really do? When we schedule a task, what do we really do? What do we schedule? We schedule the processor to that task. We schedule the processor to that task. Now, when I do non-preemptive scheduling, suppose a task T1 is now has got the processor, the CPU has been allocated to T1. Now, if another process, another task T2, which has got higher priority than T1 arrives now, all right, then in a non-preemptive thing, I cannot touch T1, I cannot do anything. So, the scenario is this, T1 came here and was started. At this point, T2 arrived. T1 arrived here and was started. T2 arrived, and T2 has got the higher priority than T1, but still, since T1 has been allocated the CPU, it will go on continuing. T2 can only start after T1 completes. Now, if it be the case that initially I have got, it is non-preemptive, all right. Now, T1, T2, T3, all of them arrived at the same time. So, the arrival time for both of them was 0, both of them arrived at the same time. So, in my timeline, I have got all the tasks T1, T2 and T3 all arrived here. Which one should I allocate? Now, that can be done in different ways. For example, in a non-preemptive scheduling, we are aware of the operating system scheduling algorithms. For example, in standard one, we have got the first come first served. Now, here in this case, the first come first served does not apply because all of them have come together. Then we have got the shortest job first, right, shortest job first. We look at, we have to have an a priori idea of what is the run time of T1, T2 or T3. Accordingly, we schedule any one of them. For example, I schedule T2. Now, once I schedule T2, now suppose T4 has come, which is shorter in length than T1, T2, T3, but it came at a time say 2 here, it arrived. Now, if my shortest job first algorithm is non-preemptive, then I cannot give any priority to this until this finishes. Once it is finished, then T2 has finished. Then I look at my remaining ones and see which one will have the highest priority, then this one will have the highest priority, because it is shortest job. So, this one will get that CPU time at that time. But in the case of preemptive scheduling, if a higher priority task arrives, for example, T1 was running here and T2 has arrived here. Now, if T2 is of higher priority than T1, then T1 will be stopped here and T2 will be started from this point. And after T2 finishes, this remaining part of T1 will be carried out. Okay. This will be done here. So, this will be pushed back here. Now, the question is, how do we decide on the priorities? The priorities can be defined either by the processes themselves. We can assign a priori priorities that this task will have higher priority over this. We can create a hierarchy of priorities, or by the scheduling policies. For example, shortest job first gives a priority to the shorter jobs, shortest remaining time first, there is another shortest remaining time first. So, that one will be again giving a priority dynamically. Now, these can be, this and this can be either preemptive or non preemptive. Now, before we will take up this blocking due to mutual exclusion in the next lecture, but let us conclude with a note on our standard priority standard scheduling algorithm, that is a round robin scheduling algorithm. Now, what happens in the case of round robin scheduling algorithm? Is it preemptive or non preemptive? Round robin scheduling algorithm means, now I can again have it in both ways. One is that I take, but round robin, essentially what happens is, there are tasks in my ready queue, all right. There is a queue which holds all the tasks which are ready to be executed, waiting for getting the CPU, all right. Now, I can select from this queue based on some priority. I can select from this queue also based on first come first served, but please note that first come first served is also a priority. What sort of priority? The priority is being determined based on your time of arrival, right. Suppose I take this task and give it to the CPU. Then along with this, in a round robin, I usually associate a time quantum. Say for example, typically 5 millisecond. So, this job will run for 5 millisecond. It will either complete if its execution time is less than 5 millisecond, otherwise it will join back the queue, all right. T1 second installment comes back here and then T2 will get it. So, this is also preemptive. The preemption is being done not because of the arrival of some other job, but the preemption is being done because the time quantum being elapsed. So, everybody has been given some time quantum, that time quantum is elapsing. So, that is being taken back, all right. So, we know now what is priority, and the standard operating system scheduling algorithms, they can be either preemptive scheduling algorithms or non preemptive scheduling algorithms. In real time environment, from the next lecture onwards, we will be looking at preemptive scheduling algorithms only initially, all right. And then we will come up with other real time scheduling algorithms.